Now I think it's time to think a little bit deeper about neural networks. We also showed you before that there are all kinds of neural networks, actually. We paid a lot of attention last time to forward neural networks, right? In these cases, it's like the vanilla neural network. You see these kind of building blocks that's passed sequentially, where the information is passed across sequentially, right? But there are other possibilities as well, right? So like what is shown here. So the first example is like here, right? You have this input, right? There's let me call it a hidden layer for the moment, but these are the hidden blocks, right? And there's actually a sequential information passed across them. And they have the corresponding output, right? So you may wonder, what do you do with this one, right? Well, this is one example, for instance, for image captioning. You have an input image here, but the output is a sentence that captures the image, right? So this is a one-to-many kind of architecture, right? We also have many-to-one in this case. Any guess or what kind of applications? Can you name one? For many-to-one. Any volunteers? One application where the many-to-one architecture may make sense. One simple example is just reversing image captioning. Start with a sentence and synthesize an image, right? A man walking his dog along the river, and there's, people sailing in the river. So that's a sentence, but I can, synthesize the image accordingly, right? Do you want to give another example? Grouping?
Tell whether the inputs are insane can be gathered in one group.
I see. But we gotta pay attention that you sort of like, you have the sequence information here. That is in the nature of the input or output. Then accordingly, in the intermediate layers, we use the sequence structure as well, right? So not sure that the example you gave has a sequence structure in the input for this many-to-one, okay? The example that was given was sentiment classification. So you can look at others' tweets and read a sentence and figure out what is the sentiment. Are they, happy or angry or frustrated and so on, right? So this is like a sentiment classification. Because in the end, it's like a categorical label, right? But the input has a sequence of words. Many-to-many. You can think of an example that could utilize a many-to-many kind of. So that means both the input and the output have some sequence information. Can you give one example? Okay, for instance, machine translation, right? You start with a sequence of words and you get a sequence of words, right? You may pay attention that you see this input-output are not really aligned to the same hidden blocks. We'll talk more about it. And then there's this kind of many-to-many where they are kind of aligned. So if I gave you an example, for instance, the video classification on the frame level. Each frame, I give a categorical label for this video, but the label of the previous frame or frames would affect my decision for the current frame, right? Right? So that's the examples for different kind of. So I think here you can probably already see two keywords. One is the sequence. There's a sequence information, right? Either demanded in the input or the output. And it's actually reflected in the architecture, right? The second one is recurrent. So we'll pay attention to these two keywords, okay? So actually, this idea is not something that we haven't learned. We already learned it. We just learned from the CNN, right? That is, utilizing some mathematical operators that actually are not just economic, but also consistent to how our vision systems work, right? Including this, localness, including this translational invariance, and so on. So we look at the convolution at the end because it really gives us what we want. But keep in mind that using this convolution kernel, it's a very small, right, 3 by 3, 4 by 4, much smaller than the, image size. And using these convolutions, we can, make this applicable to variable sizes of the images and the scalabilities of the large images and so on. And we have sparse connections, right? What I mean by sparse connection, do you remember a figure I showed before to illustrate the concept of the receptive field? I was saying that if your kernel size was 3 by 3, right? If you look at, the first hidden layer, one neuron there basically receive like input from 3 input neurons, right? 3 pixels. But then if you go down, right, go deeper, right, the second hidden layer, each neuron there receives input from 3 previous hidden layers neurons, and each of the 3 receives again, 3 of the input neurons. So the receptive field is actually very wide, given the depth. And we accomplish that through just a very sparse connections, just a local, right? 3, for instance. And we use the parameter sharing, right? So we can probably consider the same idea, but now not for the grid data, but for the image data, right? Can we use some similar ideas for sequence data? Because we desire the similar applicability and scalability for the sequence data, right? We also probably, would like to use the parameter sharing idea as well. Can we borrow similar ideas in the convolutional neural works? We have the convolutions, right? So here, can we, the convolution kernels were, the same kernel was, sliding down the grid, right? The 2-dimensional grid. Can we borrow similar ideas? Well, the keyword is recurrent, okay? So it's a recurrence formula, so it's like the following, okay? So let's consider a sequence, right, where each position is indexed, right? And this index, we can call it a time, t, right? This could be a position in the sequence. Let's call it x of t, right? And let's imagine that when t equal to 1, I have h of 0 that is initialized somehow. Right? Let's call it an old state because t is present and t minus 1 is the past, the immediate past. Right? So that's an old state. And then to give the new state, right, for time t, to calculate the new state h sub t, I'm basically using the old state and the current input vector x sub t. And I use some function which is parameterized by w. So the recurrence is reflected by the fact that I am using the same w for all the time t. So that's the recursive. You can think of what h of t plus 1 equals to. That equals to f sub w of f sub w, right? Of this one, then comma xt plus 1, right? In that sense, it's recursive. Like, did I get what I mean? the same f of w, f sub w, right? So in this sense, it's recursive. We are using this fw recursively. We are composing fw. So, and we are reusing this fw, okay? So it's a recursive formula. So I was asking, how do we share the parameters, right? So that's how we share the parameters, okay? Okay. Let's see. Okay, good. All right. So if in the convolutional neural network we use the same small convolutional kernel, right, over the 2D, 3D spatial grids, here we have a sequence, so there's a concept of time, so we are using the same formula recurrently over time, okay? So if we want to visualize this concept, right, the bottom is the input x and the top is output y, but you can imagine that this is xt plus x, this is x of x sub t, and then this is y is like h sub t, right? Then this new h sub t is going to be fed back to this RNN, right, with the new xt plus 1, and then you get the new ht plus 1, and so on. So it's like a cycle here, right? So I hope you understand that the reason I'm using a cycle to illustrate is with the recurrence formula mathematically underlying. So that's the reason, okay? Let's make sure that we understand both the mathematics and the intuition. Okay, so this is how we get the parameter sharing, right? So now let's talk about what is the f of f sub w, right? With some examples, right? So one example is like, this, weighted sum and then hyperbolic tangent. This is one idea, right? So this is sometimes called a vanilla RNN, right? And the y is simply like a linear readout of ht, which is, h is for the hidden, right? Hidden vector, right? This is a very vanilla idea, right? So now let's look at another way, right? Previously I showed you that this is what I showed you is like a recurrent diagram, right? Because I have these cycles, right? But here I'm not looking at a time index t anywhere. I'm just, implicitly I'm telling you that the previous, will be fed for the next state. There's a time concept in it, right? So in other words, this diagram was not really shown in the time, right? So in that sense, I'm saying that it's not unfolded. It's already folded. There's if you think about the time axis, right? It's like already collapsed, right? I'm not showing or extending it in the time domain. So now let's imagine that we can unfold it or unroll this into like a time domain. Now we can have this superscript t for the time index now, right? So now we're not using a single x and single h. We're actually looking at x and h at different time point. So this is like unfold or unrolled, okay? And here then again our input is x, and then this is output. Actually this is the hidden state, and there's no output readout yet. So this figure, this unfolded diagram, is what I showed you at the beginning. Right? Right? So that's what this very simple illustration is about, okay? So now you know that, you could have the math, you have the, a collapsed view, and you have the unfolded view, okay? So this is the RNN. And your readout could be just here, or it could be multiple, right? Like the examples I just showed you. And now let's remind ourselves, we learned in the last lecture the computation graph, right? For both forward and backward propagation. So what's a computational graph? Well, if you look at this one, we start with x1 and with a hidden state at time 0. We put both of them into this FW, and then we get H1, right? And we keep doing this the same, right? So these X are entering the same recurrent formula, right? The FW. And the W is actually shared for all of them, all of these building blocks, okay? So we reuse the same weight matrix at every time step. This is the forward propagation for a computational graph, okay? So now if I add the readout, right? Here there's no readout yet, right? If I add the readout, as I was showing you earlier, right? I could have Y1, Y2, Y3, Y4, and so on, read out like here, right? For instance, machine translation is one example, right? I read in English and I want to translate into French, right? So this is the example I showed you earlier, right? And that's a many-to-many. I wanted to give you a more concrete idea about this many-to-many, okay? So let's talk about this thing, right? So this is a language model, but it's at the character level, meaning that the tokens are characters, okay? Or the building blocks of the sentence is regarded as the characters, right? I'm not considering words for the moment, okay? It's a very simple character level language model. I only have four letters in the vocabulary here, HELO, right? And then the training sequence here is HELLO, right? Okay, so this model is an autoregressive model. I will show you what it means, right? So the input is HELL, and they are one hot encoded as 1, 1, 1, 1 here. So it's like the vocabulary is only 4 digits, so it's one hot encoded in this way, okay? And then, based on the vanilla RNN, we can calculate the hidden state for every time t, right? And then, we probably get some numbers here, right? Given your W, which is to be learned. And then, given the hidden state, right? And I'm gonna get some output, right? And this output is gonna be mapped or categorized into one of the letters in the vocabulary, like H, E, L, or O. And what I'm trying to predict here, the true labels are E, L, L, O. So for that, I need to learn the W for X and W for H, and WHH. I need to learn these W's so that these numbers eventually, crunch to the optimum loss function that can reproduce ELLO. So what is this model trained to do? What is this model trained to do? Minimize the difference between the input and output. And what is the structure correspondence between the input and output here? Right, so here I have ELLO, right? Right, the input is HELL, the output is ELLO, right? So this is like, of course, this is, what it means is that it's the technical word is called autoregressive, meaning that the previous state is gonna be, if you have a new prediction, right? So for instance, if you have a new prediction at position t, that prediction is gonna be utilized, fed back to the model, and then get the next one t plus 1. So in other words, you're predicting p of x sub t given x1, x2 until xt minus 1. So you keep predicting x sub t recurrently in this way. One application you can think of, right, by modeling these probabilities. So this is actually like a factorization. It's, essentially what you want to model for this language model is the joint probability of x1, x2 until x sub t, right? But you can factorize them to p of x1 times p of x2 given x1 times p of x3 given x1 and x2 until all the way to p of xt given x1 through xt minus 1. Right? You can factorize them, right? So this kind of factorization is what autoregressive is about. And one application can be something you encounter every day. Used to be when you are Googling something, but now when you are writing an email in Gmail, you also get some reminders for auto-completion, right? This is one suitable application for that, right? But in general, for this language modeling, right, is for the language generation, right? Okay, so, and then this is a computational graph to many, right? So when we have this output y1, y2, y3, and so on to yt, capital T is the largest capital T. Again, compared to the previous computational graph for the forward propagation, we have the additional readouts, right? And be careful, right? It depends, right? It depends on how this y, remember, the forward propagation is all the way from x and w to j, the loss, right? The forward propagation is to compute the loss. The backward propagation is to calculate the gradient of the loss with regard to different w's at different layers. Is that right? So if we look at the forward propagation here, we have to pay attention to how the y's, right, the many outputs, map to the losses. Okay? It is possible that you have the loss at every time t, right? Every time lowercase t, and this loss is probably by comparing the corresponding yi's and xi's or other kind of ways, right? So as the answer before that, you're trying to maximize the correspondence between the input output. So the one possibility is that the character to character level, right? There's L1, L2, and so on. And the loss is the sum over all the characters, right? So that's the complete forward propagation. The computational graph for the forward propagation, okay? Remember, it goes all the way to L. That's what the forward propagation is about. And if it's many to one, right, in this case, maybe you are just trying to figure out the sentiment behind this sequence, then the final readout is probably, figured out or mapped from the last hidden state, h sub t, and then this is your y. And there's also possibilities that you have one to many, like you have the image and you want to caption the image with a sequence of characters or words. And in that case, you have these sequence introduced in the hidden layers. Then they correspond to the words, the order, or the characters in the desired output. And, and let's put this side to side again, right? One is many to one, and one is one to many, right? So many to one in this case, you can encode this sequence, right, into a single vector eventually, right? Maybe you just read out somewhere here, right? Just like the example I gave you, that predict the y, that's for the sentiment prediction. And in the case of one to many, you're producing the output sequence from a single input vector. For instance, this is the input is, the single input. Where is my x? I think x should be, where's h0? I think x1 should be fed here. Is that right? Right? There should be x1 fed here, right? There should be an x fed here, right? And that could be an image, and then output is a sequence, okay? Okay, let's see whether there is any muddy points. So far we talked about how RNNs can be utilized in different ways and their corresponding computational graphs. Okay, again, mapping from the input all the way to the loss. But this is a computational graph for forward propagation. Now we have learned so much from the last lecture that we also need to do the computation. That means we need to use gradients, right, to optimize the loss function. And for that purpose, we need to do the back propagation to calculate the gradients of J with regard to different W's using the chain rule, right? So